on the flyer their bios, and the title of the webinar is Progress in Corrosion Modeling for Prediction, Mitigation and Repair. Just a few more words about Alan Rose before he starts. Alan's got over 30 years experience transitioning computational engineering simulation tools into daily engineering design workflow. In the 1980s, he worked for British Nuclear Fuels and implemented CFD, that's computational fluid dynamics software, as a rigorous and reliable tool for safety engineering analysis. In the 1990s, working with Rolls-Royce Inc. and the USAF, Alan acquired laser diagnostic data to develop and validate CFD combustion simulation tools for NOx and soot prediction. In the early 2000s, as an expert witness, Alan used CFD in the investigation of freight ship fires, demanding a very rigorous approach to the analysis process. Over the next 15 years, Alan has implemented electrochemical and simulation into corrosion prediction and scale-up of electrochemical processes used in manufacturing, such as electrochemical machining and surface finishing operations, such as plating and anodizing. Unlike Keith, who went to America in the early 70s and never came back, after a stint of 4 years in the USA in the early 90s, working for Rolls-Royce at the US Air Force Base in Dayton, Ohio, around the corner for the Wright brothers bicycle shop, he returned to England for 14 years, practicing as an independent engineering consultant before returning and emigrating to the USA permanently in 2008. So I'm going to hand over to Alan first of all, and if you've anything to add, Alan, about your life, please do so. So you're going to speak about computational corrosion prediction, the new discipline. Thanks very much, Alan. Okay,
thank you very much. Can you hear me okay, Alan?
Yeah.
And let's see. Can you see my screen?
Yes.
Okay, great. Yeah, well, nothing much to add to that. I do like electrolytes, especially wine. So let's get on with this. In terms of, I'm going to talk about computational corrosion analysis, and we think of it as a kind of a new discipline. So we saw in the 80s and 90s, we had stress analysis and thermal analysis, and then computational fluid dynamics came in the 80s. We have impact analysis. We have all these other tools, and I think it's only more recently we've been using similar simulation tools to look at materials and material choice. And I think one of the issues has been the availability of data. So I'll talk about how we're trying to how we've developed protocols to get the data necessary to feed these solvers. And I often think of computational simulation tools being a kind of a virtual test bed, so like Boeing or Lockheed, they always test their airplane designs computationally in their virtual wind tunnels, such as using computational fluid dynamics. And I've often wondered what would have happened if we had CFD way back when they used to just develop aircraft with trial and error, basically throw it off the end of the cliff. And I've actually seen computational fluid dynamics models of the Wright Flyer. All that said, though, from concept to flight, it only took them 5 years. So, and even now it takes, 10, 20 years to introduce a new material onto an aircraft. So they were certainly getting something right. Okay, what I want to talk about today, a little bit of an intro to the company, the kind of work that we do. Then we'll talk about computational corrosion analysis. I mean, why bother? What does it actually bring to the table? I can show you the challenges out there in new design and sustainment, maintenance, repair, overhaul, where these techniques actually help us. And I'll introduce the way we think about things is, a corrosion resistant design philosophy. What does that actually mean? We encompass that in an engineering workflow, going from simple kind of computational models to more complex 3D models. And I have a few demonstrations to show. I'll do a little demo of a very quick and easy to use tool. This is something that we developed out of a Navy research program, our galvanic corrosion analysis tool. That's essentially 1D. And then I'll show you how we've been looking at 3D issues using 3D CAD and materials off real platforms and aircraft using CCM Plus, which is a computational fluid dynamics software from Siemens. And there is around the corner a new paradigm, a way in which galvanic corrosion, for instance, is going to be addressed in the future. And I'm going to introduce you to MIL Standard 889, which should be out any week now. And it's changed the way that people look at galvanic corrosion, certainly here on this side of the pond. Touch a little bit on the science behind that. Well, as a company in background, we're very much involved in corrosion simulation. We've been established for nearly 10 years. It's our birthday next month. We're in Georgia, USA, not far from the airport. And about half of our building is dedicated to testing and gathering of material information, material characterization. The other half, we do engineering, design, optimization. You make a lot of use of computational tools. I have a cluster, dedicated machine for some of the heavyweight computing. We invest a lot of time in development and transition of these electrochemical technologies, not just the software, but we don't want to use the software just for the sake of it. There's got to be an end to it. And the end is better systems, better processes, optimized designs. And we've actually used the software to develop better hardware tools. And, an outcome of them has been a couple of patents pending on some ideas that we've had, because it gives you a tremendous insight. And then we make our bread by consultancy as well. Keith, we'll be talking later. His expertise is in coatings and materials, and against a backdrop of legislation such as REACH and OSHA and EPA. So here we are, there's Georgia State, and we're just a few miles away from the airport. So, okay, so we're a small company, but we have a mission, and our mission is to help our clients quickly develop, qualify, and implement corrosion-resistant materials and coatings that, at the same time, meet the regulatory requirements. And I'm going to show you how we use our computational tools to reduce this development time. So we really leverage them, and that's where we bring something different to the table. So why am I bothered about corrosion? Well, clearly, safety. You don't want things falling off your car or your airplane. And there's a lot of snippets out there. It is a very expensive situation. An impact analysis showed that worldwide, the cost of corrosion is $2.5 trillion. Some liken it to like 2-3% or so of global gross domestic product. And it's interesting that several of these studies have also shown that a large percentage, 15 to 35% of the cost, can be saved by implementing corrosion control and better design practices. So if we were to drill down, we do a lot of work with the Department of Defense, the DoD, and just in the military, their annual cost of corrosion is $19 billion, and half of that is due to aerospace assets, the Naval Air Fleet, US Air Force Air Fleet, Army helicopters. So it's an enormous amount of money. It's interesting to know that whenever you do a design, it's estimated that once you've locked in that design, you've also locked in 70% of your sustainment costs, the costs of operating that. So, decisions made early on are really going to stick around and hurt you later on. In fact, just this year, I saw that the US Navy estimates that 40% of corrosion costs can be eliminated by better design. That's a huge amount. So more upfront work, I think, is definitely justified. From a military perspective, you want your planes ready. You don't want them in the repair shop. And a couple of years ago, FA18 had a readiness level of only 50%. It's now recently they've got up to about 80%, and it's quite an old platform. So readiness is important to some people, and commercially readiness is important. Flight delays, I found a figure, flight delays in 2007. I mean, there'll be all sorts of reasons, some repair and some corrosion. It's not all corrosion. Flight delays, aircraft on ground costs 31 billion in a year. So very expensive. So how do we tackle this? As many materials are used, as ways of looking at the design, different corrosion protection schemes, and all the time the materials that we use are being reclassified. And no sooner have we got ourselves a new coating, and Keith can talk about this, it becomes banned because they discover it's toxic. So there's a speed of innovativeness in terms of coatings, and we have to catch up with the speed of being able to deploy them and get use out of them before they become banned. Why am I interested in corrosion? Certainly from our perspective, it's actually the law. Corrosion Prevention Control planning is actually mandated in the US code. And this kind of flows through to right down to the vendors and designers and those folks that design and sell platforms, whether it's Lockheed or Boeing or GM or whatever. There are policies. The DoD have directives. It's kind of puts in place the policies, and then there are instructions on how to go do that, and specific instructions. One of them is the prevention and mitigation of corrosion on DoD military equipment and infrastructure. It's actually law that you have to put in a plan and outline to the person that's going to buy, or the organization that's going to buy your platform, how you've tackled corrosion. And then standards are more specific kind of technical guides on how to actually avoid corrosion. And I'll come to a couple of them on the military side. I mean, even though the military specs, these are public domain, they're very useful and people make use of them all over the world. I'm going to talk about this 15668, which is kind of, I would call an overarching military standard. And then there's a very specific one, galvanic corrosion, the dissimilar metals. So I mentioned the MIL standard, 1568D. Actually, in that standard, it says that modeling and validation testing shall be performed to identify corrosion-prone locations. And then later on, it talks about testing and being able to, get similar material assemblies and techniques to look at corrosion protection schemes. So it's interesting in this first paragraph where it actually says modeling. So we're talking about computational modeling, ways of trying to identify corrosion-prone locations. So you can't go do physical tests like in corrosion chambers until you know what pieces you need to test. So you need to look at the whole assembly. So you need to interrogate the whole CAD scheme, the 3D model of that airplane or whatever the components are, and try and figure out where corrosion is likely to occur before you can even frame a testing protocol. And then this MIL standard also calls out other specific ones, one of them being 889D, which is for galvanic corrosion, dissimilar materials. I'm going to talk about that in more detail. It doesn't actually call out the revision. So my inference is that it will always assume the latest revision, and D for Delta is coming out this summer. And that's going to be quite a paradigm shift. I'll just kind of touch on that now. In MIL standard 889D, for galvanic corrosion between dissimilar materials, not just metals, it can be materials and carbon fiber composites and metals and alloys. Even sealants contain metallic particulates that can make them conductive and cause issues. And essentially, rather than the traditional galvanic series, of potentials, so if there's a big potential, it's been assumed that there's a big risk of corrosion, and the converse as well. They're actually using polarization curves and using a mixed potential approach. Essentially, you get polarization curves of different materials, you see where they cross, and you actually calculate the galvanic corrosion current. and through Faraday's law, the corrosion rate. So it's a completely different way of ranking and assessing risk. And that's actually going to change very soon. Okay, so the challenges, either in new design or in sustainment. That's my excuse for putting an airplane up here. So we have, if you have a brand new plane, rolls off the factory floor, pristine, all the coating stack-ups, all perfect, no corrosion whatsoever. But we always need to remember that these planes will fly in very hostile environments and very varied environments. So once it's out there in the field in sustainment, you see corrosion everywhere because the wings will move and flex and you'll get water penetration and all those protection schemes. In the old days, we used cadmium as a sacrificial coating. It does eventually get consumed, and then there's an impact on other adjacent components. And with modeling, computational modeling, we can look at these what-if scenarios. An important aspect, of course, is the environment. So there's a big difference between an airplane spending time in Guam and spending time in the desert in Nevada. We've had there's a company, Luna, that have manufactured sensors that have been on board planes, and you can see the cycle of humidity and temperature that a plane would pass through. And different tail numbers can have different lives. So it's not just, oh, let me do a corrosion analysis for my 737. A Boeing 737 actually is also a military version, is a P-8 Poseidon, which is a sub-hunter, which flies very low over the ocean, in a very salty environment. So it's important to know that even from this, using the same plane, from one tail number to another tail number, they can see different environments. And then there's sporadic environments as well, very harsh, where you literally get thousands of tons of salt water just dumped on your planes in these storms here on the Kitty Hawk, for example. So, Alan, can you still hear me?
Yeah, absolutely. I've just posted, I should have mentioned at the beginning that if anybody's got any questions, then please post them in the chat and Alan and Keith will answer them later. Thank you.
Okay, very good. All right. All right then, so there was an F-18 there on deck, and if you was to open up the panel on the F-18, carbon, you got composite panels, and underneath there you have this aluminum structure and a lot of interaction, very nasty. So all these fasteners, these steel fasteners, interact with the aluminum airframe and the carbon fiber composite and cause corrosion. And this is important. Galvanic corrosion, there are many mechanisms of corrosion. We're particularly interested in galvanic corrosion because 80% of military structural failures are actually initiated from corrosion pits. So getting a handle on that is very important. So all this has to be repaired, and that takes time, and it's very expensive. It's very messy. So here's one example of a repair method where you have to remove the corrosion. Of course, that changes the size of the hole, so you may need to bush that. There's a couple of different ways of doing that. You can freeze it in liquid nitrogen, or you can do a cold form fit here with force mate. The point being that every one of those holes has to be fixed. That's an awful lot of labor and expense and takes a lot of time. So we need ways of avoiding that. And, no matter how modern the platforms have been, F-22, for example, there was an issue overlooked there where there was an interaction between conductive gap filler and aluminum skin panels, which caused a galvanic corrosion interaction. And essentially, that one repair across that fleet was more than $228 million. So it's very expensive. And that could have been identified with the tools that we're going to go into and present to you shortly. There are many more examples of issues on board amphibious assault vehicles and ships and so on. So clearly we need some good computational tools that can identify these potential hazards early on. So corrosion resistant design philosophy, what do I really mean? Well, the first thing, it's kind of a common issue really. If it can go wrong, it will go wrong. So coatings and materials will always degrade. and they'll always become damaged. You know, people drop spanners and scratch coatings and all sorts of things. Very rough treatment, certainly in the military. So it's vital that we have tools to look at what if scenarios. Let's assume that failure is going to happen. Let's assume that damage and degradation will happen, and then follow what ensues. And then maybe we can make better decisions. How do we actually tackle corrosion issues once, you know, it's one thing predicting them and finding them. How do we actually tackle them? And we can have different treatments and so on. Keith will touch on this later on. But what's been used in the past is cadmium, wonderful, unfortunately toxic, and chromates. And there's different ways of, you know, physically inhibiting corrosion. But now as we get new materials, we want to be able to put them through this design process much more quickly in order to get to a champion material that's going to help us. And as I've mentioned before, corrosion prevention control planning is a requirement. So you need to incorporate modeling into your design work. Okay, so this is our view of the corrosion modeling world. We have an environment. We've teamed with Siemens, software company. They have computational fluid dynamics, star CCM+. And over here on the left, we think of a flow. You know, it's like whenever I'm doing an engineering calculation, it's like we call it the back of the envelope calculation, or, you know, some Excel spreadsheets or MathCAD, and, you know, you kind of go step by step, increasing complexity, because you might be able to sort out and iron out some issues early on. And that's the same way that we approach our work on corrosion analysis. So we have Corrosion Gin, which is the Corrdesa software, and you'll be able to access it either directly, I'll show you in a moment, or within the environment such as Teamcenter, which is a PLM software, product life management software. So what we can do, we can use Corrosion Gin, and very, very quickly you can look at different materials. Hey, I've got some steel fasteners here, aluminum frame, what's the issue going to be? And you can look at the impact of different treatments. And I'll demonstrate that in a moment. Maybe it's not as simple as just this anode to cathode area ratio analysis. I need to take into account the geometry. And we have a way of setting up kind of fundamental building blocks, certainly for the aircraft, lap joints, bushings. We can put in some dimensions, and we can do a very quick 3D analysis for a small family of different kind of geometries. And then we can just pull in the whole CAD, do the whole analysis, and get the corrosion rate for the complex geometry. So I'll show you some examples. Okay, so here I'm just going to jump out to Corrosion Gin. Okay, so this is Corrosion Gin. You can access it on the web. That's software as a service. That's how we do it. It's also available through a couple of different third parties. So let's assume, for instance, the scenario is your M&P engineer is looking and interested in the issue of fasteners, just like on the F-18, the aluminum structure, and reducing galvanic corrosion risk. So we can choose the environment. I'll choose a 3.5% sodium chloride as a marine type environment. We'll be able to do the MIL standard 889D data as well when that comes out. So we consider them in material couples, and we describe each material substrate designation, coating, treatment. So substrate is like, you know, the element or the alloy, so aluminum. Designation could be the type, so 7075 T6 for my example here. Coating, anodized, let's say no for the moment, so I can show you the resolution that we have here. And then we'll go for a stainless steel fastener, 15.5 pH with no treatments. So this has an electrochemical database. It pulls those curves, it finds out where the intersections is, and it tells you what the corrosion rate is. So over here, this first group shows that aluminum alloy is anodic compared to the stainless steel, which is cathodic. And we've got the self-corrosion. So the self-corrosion rate of the aluminum alloy, and we have a self-corrosion rate over here of the stainless steel, which is clearly very low. But if you were to combine these, the galvanic corrosion is 123 microns a year. That's just the issue. You've got an acceleration factor, you could say here, of almost 7 because of this galvanic corrosion issue. Okay, we don't like that, so I can copy that. And now I've got myself a new group, and it's automatically populated, and I'll modify. And I said, well, really, the aluminum alloy would be treated. So let's anodize it, chromate seal. We'll key the stainless steel fastener, click the button, and what will happen here now is the corrosion rate has gone from 123 to 85. Now, anodizing is really for a kind of a general area protection. It doesn't really protect you very well for organic corrosion, which is very intense and very localized. What would be better and cheaper actually would be to consider the fastener material. So we can copy this again, modify the group, and let's go over here. Let's change stainless steel for titanium, Ti64. And very quickly, we find that the corrosion rate here is less than 2 microns a year. So that's an example of using Corrosion Gin to quickly kind of get a feeling about the different materials, impact of the different surface finishes, and so on. Let's go back over here. Okay, so what we did, I just showed you Corrosion Gin, how we looked at impact of different materials. It's interesting that generally, if you were to look at like the older standards, the potential difference, looking at potential differences, folks would think that titanium isn't a very good choice. But in fact, it is, because if you look at the polarization behavior, because of the resistive layer onto titanium, it just doesn't corrode when adjacent to the aluminum. So what we find that very quickly, we compared a bare aluminum alloy, anodized aluminum alloy with different fasteners. And you saw how quickly we could do that and then come to a conclusion, oh, this combination might be better. Using the old military standard, you wouldn't get that solution and you'd miss out. Okay, so that's the quick 1D analysis. Maybe we want to do something more complex. We try to capture common fittings such as bushings, shafts, lap joints and butt joints. And we can enter dimensions in here and very quickly, using the CCM Plus software, come up with a corrosion map, the corrosion rate map. So that's kind of limited, but it gives you a little bit more fidelity. But if you have the full CAD model, you can actually really deep dive. So here's an example where we did some work on F18, leading edge flap actuation system. It's very complex. You have a lot of moving parts, a lot of different coatings, different materials, and this can get quite exposed as well. So it's difficult to think of a priori which piece is anodic, which piece is cathodic, and so on. So you just put all that data into your model. The workflow is very similar to a thermal analysis or a stress analysis. My background is fluid mechanics. So you get the geometry. If it's legacy geometry, this might be old 2D drawings, but you need to make a 3D geometry, which on new products is no issue at all. You can scan this, 3D scan it as well. We've done that. Once you've acquired the geometry, you assign the materials, your aluminum, your stainless steel, so on and so on. We're looking at a bushing and a lug, for example. And that will, under the hood, pull the appropriate electrochemical data. And then you can, there are several different electrochemical solvers within the CCM Plus software, and you can solve for the galvanic corrosion. You solve for the potential and the current density, and you can figure out what the corrosion rate will be, given the material information. Now, a further advantage of going with a full 3D is now, think of this assembly as being wrapped in like kind of cling film, almost like a a uniform covering of electrolyte, because that's what you need for galvanic corrosion. There needs to be like an electrical circuit. And what we can do, we can look at the impact of whether the electrolyte is kind of thick and in bulk, or whether it's a thin film. So we have polarization curves here. The gray is aluminum alloy. And if we have the polarization data for a kind of, a deeper electrolyte covering, then the corrosion current is much, much smaller. This is corrosion current on the top. So going to the left, it's going smaller. Whereas having the polarization curve for the 50 microns, you will find that the corrosion is much more intense, a couple of orders higher. So we can deconvolute this bulk data to get any kind of thickness polarization curve, at any other thickness. Why does it make a difference? If it's a thin electrolyte, then you're getting more oxygen diffusion, and that increases the kinetics, and it's a lot more aggressive. So you can actually count for that. So that you find on your lug here, you got much more intense corrosion here on the right when it's covered with a very thin film compared to just dropping it in a bucket. So it's intense and it's localized, and this is what we see in reality, and we can predict it in these computer models. So I talked about the 1D approach, Corrosion Gin. Also talked about this 3D approach using using the CCM Plus software with the appropriate data. At the interface, the current density is the same because you're using the same data. That's the beauty. We've got this database. We can either use it in Gin or we can use it in 3D models. It's the same electrochemical data. You just get more information out in terms of how that corrosion peaks near these interfaces and kind of dies off. Another example here, this is an interesting one because then we can look at how corrosion might progress. So F18 again, and we're talking about the wing attached bulkhead. And what we have here is this very large structure, these pins that essentially hold on the wing. And we zoom in here on that structure. So take a look closely here. We have this steel pin, but it's cadmium coated. So the red is cadmium coating. And then here there's a kind of an annulus that's showing the bushing, and that's cadmium coated as well. And then we have the aluminum structure. And here's a result of some analyses. Just a quick check, Alan. You still hear me okay?
If I put my microphone on, yes.
Okay.
Yeah,
I just like to make sure I'm not talking to a vacuum.
No, it's very good, Alan.
Okay. All right, and so let's look at these in a clockwise direction. So initially, the pin and the bushing is cadmium coated. Now we've got a high current density, which is red, which is proportional to corrosion. So this corrosion is actually beneficial because what's happening here is that the cadmium is corroding sacrificially. And the aluminum lug, our big expensive structure that we want to keep safe, is pristine. But as time progresses, we'll look down here, eventually the cadmium on the bushing could get damaged or certainly get consumed, but still not an issue because the cadmium on the pin is still protecting and has enough throwing power to protect the aluminum despite this copper beryllium bushing in between. But eventually the cadmium is consumed enough on the pin that the whole thing flips. And this copper beryllium bushing being so positive has a big impact on the aluminum and starts corroding intensely this aluminum lug. And as you can see over here, very, very nasty, very big, expensive structure. So, knowing how things might proceed from your pristine T0 condition can really help you design that stack up in those materials. We've thought about how you can deploy, whether it's Corrosion Gin or this corrosion modeling capability across an enterprise on something very interesting that we've learned is, and you could scale this down. So there's a large organization. In fact, I saw a presentation, I think it was like United Technologies, and you can have thousands, I think over 100,000 for them, product engineers, okay? So say you have 15,000 product engineers, and the fact is that these engineers make day-to-day decisions that impact the design and impact the corrosion, even though they may not be materials experts. When it comes to materials, you have a fraction of that actually people that actually have materials expertise. And then out of them, so out of that 1,000, we got like 45 corrosion engineers. These guys are very, very busy when it comes to materials. So you can deploy this kind of capability in such a way that you provide your engineers with a safer sandbox, you could say. So they could run these tools. The tools could be, super administered by the corrosion engineers, the folks that know the information, and they can make more and more decisions and better decisions on product design early on in the design without having to pick up the phone and talk to these guys all the time. Likewise, maybe the materials engineers come up to some issue and they have an amber moving to a kind of a red warning. Maybe you should talk to a corrosion engineer. It might not just be a material choice. Maybe you need to look at some design issues. So there's ways of actually deploying this. And this is one thing, one of the reasons we teamed up with Siemens and Teamcenter to deploy this data and this capability in these kind of organizations. Okay, so I mentioned the MIL standard 889D and I'm going to introduce mixed potential theory and how that's now being used in the upcoming standard and how that might make an impact and hopefully give us much better tools. So in 2018, NAVAIR, the Naval Air Fleet, Victor Rodriguez Santiago, he presented the issue here. I've already touched on it with titanium and stainless steel. So kind of in the old days, I mean, this is very, very old. I think Keith knows. He tried to track this down, how old this potential series is. What we're looking at here is the potential moving horizontally. So as we move to the left, the materials are becoming more and more active. So we have zinc and aluminum alloys here towards the left. We have our more noble materials and graphite towards the right. So traditionally, the larger the horizontal distance, people have thought that there's a higher risk of corrosion. But for titanium, it actually flips, because when you look at the curves over here, looking at stainless steel and aluminum and the titanium and aluminum couples, and we look at concentration of the salt, and we have the galvanic corrosion current that we find for stainless steel and aluminum, these corrosion currents are much, much higher compared to titanium, which is the converse when you look at a potential approach. So this clearly needs to be tackled and was proposed to be tackled in this MIL standard. And here's proof in the pudding, really. We have titanium fasteners, aluminum 2024, and stainless steel fasteners, and the corrosion is around the stainless steel. So what they proposed was a new approach where they would actually calculate the galvanic current, not look at the potential difference. And we do that by looking at the polarization curves. So the standard now is in its draft form, and it's actually introducing and opening the door for computational approaches using these polarization curves. So when we have the polarization curves, what I'm showing here, the solid curves are the aluminum alloys, bare or treated, and the dotted curves are like fastener materials such as stainless steel or titanium. So traditionally, people have been looking at the potential difference between these couples. So you see the potential difference between titanium and aluminum is much larger than that between stainless steel and aluminum. But as I pointed out, where the curves cross, you actually have a lower current for where the titanium aluminum couple crosses compared to the stainless steel. And that is now captured in this new standard. So Last year, they updated their approach. It's a very long process, developing and revising a military standard. So we had 889B, and then they modified it and started changing terminology in 2016. And this year, we expect the draft has been out to consultation. It's come back, and they're just kind of dotting I's and crossing T's, and this standard will come out very soon. There are reasons that are numerous, and you can look at these at your leisure in the recording or printed version. I guess one of the main things is a criticism of the previous mill standard was there was little quantitative data and guidance. And the fact now we have a more fundamentally correct approach, which takes into account the kinetics and how intense the corrosion might be. So the mill standard will look like this. This is like it's quite an eye chart, really. It's like the mileage charts we use as kids to figure out, the distance between London and Manchester. You look at your alloys here, and they're all numbered. So you can just read magnesium against, say, the pH 17.4 here. So I'll go magnesium up to 38, and it's quite high corrosion. And they've classified it here. Here are the corrosion rates. Okay, so people will say, well, what is a bad corrosion rate? And the answer is, well, that depends. What are you designing? I can take a little bit more corrosion on the ground in a car compared to on, an airplane in the air. So it really depends. So they've given you that flexibility, but still provided quantitative information. And it's not just the bare materials. They also have data in here on the impact of different treatments, chromate treatments, and so on. And also they've made comparisons here between these various alloys and those treatments, and even some carbon fiber composites. Now then, the reason I guess it hasn't been done before is you still need to gather this data. How can you be sure that you gather the data in a robust and consistent manner? And a big part of the work was we were involved in this with the Office of Naval Research and published best practices for corrosion data acquisition. And then this was modified, and is actually going to be was modified by Navarre and the team there at Pax River, and is now an appendix to the mill standard. So essentially, one criticism is, well, as soon as you print a military standard or any standard, it's out of date. And we know that we have to develop materials very quickly in order to get them in before they become illegal, because they become toxic or something like that. So the standard actually tells you how you can gather information and acquire it in a standard way for your own materials, whether they're kind of proprietary or they're just new materials. I can share that. Okay, key influences on corrosion. Just a few more minutes. I'll just touch on some of the science underneath this. A way I look at this, we have our chemistry, of course, that describes the kinetics, how aggressive that chemistry may be. 5% sodium chloride is more aggressive than 3.5%, for example. Then the hydrodynamics I've touched on. Well, is it a thick film or a thin film? Because when it's thin, you've got oxygen diffusion. You've got to take that into account. And then the movement of electrons and current. So we have the electrodynamics aspect. So all these are taken care of essentially in the computational model. You can calculate what that resistance, that impedance is. So that's exactly, when we look at polarization curves, for instance, for 3.5% sodium chloride, we find that what we're looking at here, the gray is aluminum, and we have our bulk stainless steel, as I showed you before. And here we have the thin electrolyte. Big difference, very, very low for the bulk electrolyte in 5%. The picture's different, sorry, 3.5%. The picture's different when you look at 5%. Now, whether it's thin or thick, the corrosion's very aggressive. And this is interesting because if you're familiar with these tests like the ASTM B117, it is a very intense, a warm, intense 24/7 test. And it gives you no fidelity whatsoever. components will corrode in there, fine, but they don't give you an indication of what they're going to actually look like when they fielded. There's no fidelity. It doesn't know the difference whether it's a thin layer of electrolyte or a thick layer. It just corrodes the hell out of it. So mixed potential theory, my kind of simple view on it. Let's have a look at a simple couple, iron and copper. So we connect these, and the iron essentially will oxidize, losing electrons, oxidation, if you remember your high school physics. And the copper, you have a reduction reaction where you gain electrons, and that's reduction. And as my niece recently said, she uses oil rig, oxidation is losing and reduction is gaining. But the idea is that there's a circuit set up. And the way I think about it, when you think about Ohm's law, which is the relationship between potential, current, and resistance. So the potential, the current times the resistance, okay? And there's a circuit here where you have a resistance due to these reactions on the surface. You have a resistance, the impedance drop in the electrolyte here. And then you have resistances due to these reactions. So it's an electric circuit. And the way I like to think about it, of course, from the copper to the iron is virtually zero resistance compared to all these other resistances. So you can have a large potential difference because of a large current and a small resistance, so a large current being a large corrosion, or you could have a large resistance, which, like in the case of titanium, if you have the large resistance, you have a small current, and hence, the titanium didn't cause as much corrosion on the aluminum. So we have the polarization curves. It's based on the principle of charge conservation, avoids the accumulation of charge on the freely immersed electrode. And essentially, we can find the crossing point of different material curves. And at that crossing point, we have the corrosion current and the mixed potential. So we get that information out of this analysis if you have the data. Okay, so to summarize then, what I've thought about, we've had electrochemical simulation capability for a long time. And in the CCM Plus software, there's three kind of solvers there: primary, secondary, and tertiary current density assumptions, they call them. And they've been there for a while and maybe not used as much as they could be. And I liken it to like having a fantastic car, really fast car, but having no, petrol or gasoline. And now we have the data. So now we have the fuel. So data is key. With the electrochemistry data, you can look at the kinetics. That gives you a more quantitative and more accurate corrosion rate prediction. We can do something very quick with the curve crossing technique, with Corrosion Gin. With that same data, we can go deep dive and do the 3D analyses that I showed you. And I like to think of this as really just, instead of the virtual wind tunnel that we have, that we could do with the Wright brothers plane, we now have a virtual accelerated corrosion chamber that reflects what can happen in the field as a simulation. So these whole tools can reduce those options. You still have to go do some physical testing. That's what is required by the standards. But rather than doing thousands of tests, you can reduce that to a much, much less number. Okay, Alan, I can finish it there and take questions, or we can have a break, or whatever you want to do now.
We've got some interesting questions, Alan. So what I would suggest is we just take these questions and then we give everybody a break, time to grab a coffee and come back for Keith when we've taken the questions. So Pamela's going to read the questions to us. Are you ready for this, Pamela?
Yes, indeed. So first question from Peter Darnley. What are the fastener materials and coating materials that are used to join aluminium alloy skins to the airframes you showed? Also, what are the wing spars made of?
Okay. Keith, I don't know if you want to take this question because you're closer to the materials in terms of skin materials and structure materials.
Yeah, yeah, sure. I mean, typically in older aircraft, the fasteners are high strength steel and they're CAD plated. That's the standard. They're now becoming more fasteners made out of titanium, Ti64, which is they're not plated. The alloys in the aircraft, typically again 7075 T6 aluminum for the spars, and 2024, which is a copper-rich alloy for the skin. And so skins tend to corrode very easily. It's a real problem.
Okay.
Okay, thanks, Keith. Pamela?
Another question. Titanium alloys have excellent static aqueous corrosion resistance, but if there is any fretting in the application, the story is very different. What's your opinion?
Keith, I'll pull this on you again. You're the materials guy.
Yeah, well, of course, with fretting, what happens then is that you've got two materials generally rubbing very slightly against each other, and you tend to get very rapid damage, loss of the oxide coating, which tends to give you that nice corrosion resistance. And so, but now what you can then do is in computation, you can take that into account by then saying, what happens if I make a hole through this nice area here, or rather a damage on this nice area here? Now, what kind of corrosion rates do I get? And how do I deal with that?
Okay.
So we can take that into account.
Yeah.
Question from Nasta Sanchez. What is the coating thickness range for this application? I think I'm not sure which application he was talking about. Maybe he can unmute himself and talk about it. And what is the visual technique that is used to measure it? So I'm not really think.
So this was 38 minutes into the talk.
Yeah.
If you can remember what you were talking about at that point.
Well, shall I take this one again, Alan?
Yeah.
They're talking about
go
coating
on.
thicknesses, and typically, actually zinc nickel is the new coating taking over from CAD, but they're both about the same thickness of about 0.5 of an inch, 0.25 of an inch. In other words, 5 to 12 microns. And then on top of that, you've got a paint system, which is also a coating system, which altogether between primer and top coat is typically about 0.02.
Okay. All right.
Okay, Pamela.
I think no more questions.
We got another
oh no! Oh, yes. Sorry. Alexi asked a question. For calculation of galvanic current using polarization curves, perhaps net current rather than the current density should be used, and there is a question mark. So he's asking a question. So shall I repeat the question again?
Yeah. No. Okay. Let me think about that.
Yeah. I mean, we use. Go ahead, Alan.
No. Go on. Say.
Yeah, we use current density rather than total current, because the current density tells you what is the corrosion rate at that area. In other words, the corrosion per unit, per unit depth, and that gives you a better idea of how deep are those corrosion pits going, which is the thing that you're always worried about.
Okay, and what you can do is, if you have a map of the current density, then using Faraday's law, you can then integrate over that whole area and find out what your volume loss is, and hence what your mass loss is. So I think the main thing by mapping out the current density is that you can get the localized information as well as that integrated information on total corrosion.
Okay, thanks very much. We'll take a couple of minutes for a comfort break, if that's okay, and then reconvene. Let's make it fairly short. Shall we say 5 minutes?
5 minutes.
Yeah.
Sounds good. Yeah.
So we'll have Keith to entertain us.
Yeah.
That's just enough time for you to get your hat and cane, Keith.
That's right. Yeah, I can do that. Right.
All right.
5.
I mean, by all means, if anybody wants to continue the discussion, if you want to unmute yourself, Alexi, if you wish to expand on your question while we're we're waiting, by all means do that. I'm not sure if your question was addressed.
Hi, Alan.
Hello.
Hi, Keith. Yeah, the reason why I asked the question is that the situation with, for example, fasteners will dramatically change if you've got the fasteners acting as an anode or cathode. Because the if you've got corrosion of a fastener, then it is a small surface area, and therefore it will result in a very, very large current density, and it will corrode faster. And vice versa, if the anode is your structure, then the corrosion current density will be very, very small, and it wouldn't make any damage in the case of galvanic coupling. Therefore, net current densities, net currents rather than current densities should really be used, unless you do the 2D or 3D modeling of the current density distribution.
Mm-hmm. Okay. Yeah, well, like you say, we can do the 3D model of the current density distribution. And I think from those charts in the mill standard, I think they might have calculated, the actual current, the integrated current between the area to cathode ratio of 1 of those two components. So I think
yes, exactly, but that's never been the case. That's the area of anode and area of cathode are always different in practical situation. And that's the key for the galvanic coupling, that you rather have a large anode and a small cathode so that you minimize the damage by corrosion.
Yeah. Yeah, so when they planned the release of that mill standard, they saw kind of a development path, and that mileage chart, it comes with caveats. Those being, the assumption is anode to cathode area ratio 1. Okay, so you got to bear that in mind. Now, in a bulk electrolyte and something like the sodium chloride 3.5% that's very conductive, you can do a little bit of scaling without too much error. But if it's a thin electrolyte, then the only way to take into account the difference in those areas is actually doing the calculation and solving the Laplacian for the current density, and you can do that like you suggested with a 3D model. So I think with the 3D model you can capture those effects if you have the polarization curve for the electrolyte and for the electrolyte at that particular thickness.
Thanks, Alan.
Okay, thank you.
Thanks very much. Pamela, is our 5 minutes up yet? I think Pamela's probably gone to get her coffee.
Probably has, yeah.
Sorry, I'm back.
Right. Are we ready to go with Keith?
Yes.
Right.
Yes, I guess so.
Okay.
Excellent.
Right. Thank you. Thanks everybody for joining. We've got some very illustrious guests with us in this. We've got professors from all over the world and friends who we haven't seen for a while. So that's excellent. Right. So Keith, are you ready to go?
Oh yeah, I'm fine.
Always. And I pointed out earlier that you've decided to confuse us by having the Eiffel Tower behind you.
Yeah, I like to call him from Paris when I'm over here.
So just some background to Keith. I've known Keith for, well, many, many years. He went to the USA in 1973 for a 2-year position, and somehow he says he never made it back to the UK. In the 1970s, he started one of the first companies doing ion implantation for metals for intermetals for wear resistance. And that was a technology that was first pioneered by a guy called Jeff Durnley at Harwell. In brackets here, because I'm reading what he sent me, it says it failed miserably as all the others did. And you're absolutely right there, Keith. How many miracle coatings and treatments have we seen over our lifetime, most of which came to nothing? I could actually tell you 2 or 3 that are well hyped now, or even probably 4 or 5, which will probably suffer the same fate when all the research money dries up. Anyway, that's digressing. So Alan and Keith started Corrdesa to bring corrosion analysis into the 21st century by combining Alan's knowledge of computational methods with Keith's knowledge of coatings. And Keith's primary work is with coatings and surface treatments, in particular alternatives to toxic materials such as hexavalent chrome and cadmium. Keith was technical manager for the US-Canadian hard chrome alternatives team, which brought HVOF coatings into production in the aerospace industry. Keith is a DoD subject matter expert in hexavalent chrome and supports the DoD SCRDP, ESTCP Environmental Office on coating and REACH issues. He's also an advisor to the F-35 program and assists its Corrosion Prevention Advisory Board on choice and performance of coatings alternatives. And I'll pass over to Keith, who will entertain us.
Yeah, okay. Well, Alan's going to drive, and so because we know it all works from his computer. So
it works from Pamela's.
Yeah, and it works from Pamela's too. Yeah. Okay. So yes, do you want to hit the button, Alan? And...
Yeah. So can you see your title screen there, Keith?
Yep, I can see it.
Okay.
Okay. So what are we going to cover? We're going to be talking about primarily brush plating and anodizing, and why that's different from other things, and why we're doing all this, and what is it that connects those two things together? All of this work we do that Alan talked about, with all of the computational work and all of the coatings work, and the join between them is that we couldn't do the coatings work without the computational work, because these things are getting quite complicated now. So we'll discuss the differences between different processes, tool design, a few videos because they're fun, and where do we go from here? How do we scale this whole thing up? So next. All right, you saw that movie that Alan showed of that wave crashing over the Kitty Hawk, and this is the result. And he showed some of those too, but you can see how bad this corrosion is once you take the skin off an airplane like an F-18. It's terrible, especially in those holes. So I think you'll find a couple of things come up, Alan, if you hit there. Okay, so what people tend to do is, see how many hundreds of holes these are? Now imagine drilling each one of those out and putting a bushing in it. and that is what they have to do. But the guys in the depot, they hate titanium. It's a real pain to machine. So but we got plenty of 15.5 hanging around. We use that instead. And of course, the result is that you end up with an enormous amount of corrosion around those new bushings. Whereas had they used titanium, they would have done pretty well. And generally the fretting issue and things like that isn't really an issue here because these things don't move. They don't rotate or anything. So, more than 80% of the military aircraft failures, the structural failures, initiate at those corrosion pits. So it's really important to get rid of them. Okay, next. So what do we do? As Alan was saying, we do a lot of corrosion analysis, and we use some of the fancier techniques like star CCM. I like Corrosion Gin because even I can do that. I leave the other stuff to the clever people. But then, of course, we use also the computational methods for tool design, for electrochemical tooling of one kind and another, tank plating analysis, and so on. So next. Well, I expect most of you have seen these things. You know, this is an example of a big plating plant, and you go from tank to tank to tank down the plant and put different things on as you go. Very large scale, you can do enormous things this way. But a lot of what we're seeing is more and more electrolytic processes. You know, we got electroplating lens, we've got anodizing. We're just dealing with something for a client that has to do with some cleaning and stripping, some electropolishing. We've done a fair bit of work on actually electrochemical machining, which is like corrosion gone mad. And Alan can tell you all about that. All of these things work very well. But once you've got things on a plane or a ship or a vehicle, yeah, you can take some parts off, but you can't really take the wings off so easily. Although, as you saw, you can do it, but you can't put the whole darn lot in a tank. So you need a localized method of touching things up and fixing them. And here's an example from the Navy. They do a lot of naval aircraft. I keep telling them if they quit flying on aircraft carriers over the ocean, this wouldn't be such a problem. But anyway, they do. And so they use what's called selective or brush plating. And generally it's some material, stuff that's made by Sifco, and they've made it for years. They're very good at it. And you can do plating and anodizing with localized little tools. And that allows you to do things actually on aircraft. So next. All right, this is an example of what happens when you do this kind of plating. There are two ways to do it. There's the quill pen method, where you dip and you plate, you dip and you plate, and that's one way. Or there's this method, which is the flow-through method, and you can see how much of this electrolyte is pouring down off the thing that you're plating. So, how do you deal with that? You have to catch all that stuff. And by the way, to the left of this guy, I only just noticed on the table are the little dip and plate those things. See the little red handles? That's what you do for the local touch-up. Okay, next. So, yeah, if you hit that button, I think it'll run. Yeah, okay, this is just another example. And this is, again, what the Navy does here is this is a tool for plating. But you see what he had to do? He had to get into the inner surface in those grooves first, and then he had to do the outer surface. And this could be a real problem. I mean, it isn't easy to get into things like this. And then if you've got holes, you have to do it again a different way. So, but it can be done, and it's used quite widely. So next. All right. But when you start working on a plane, if it can be very, very complicated, because now you're not just got something that you can just put in a lathe and run the way that they did in those pictures. You've got to make sure that none of that electrolyte ends up inside the plane or in the electronics or dropping down the wheel wells. And so you have to put up all kinds of barriers and channels and catchments in order to keep all of this aluminum foil. We've seen people doing this. It takes them hours to prepare a plane to do this kind of thing. So the issue there is, gee, wouldn't it be much better if you didn't have this stuff flowing everywhere? Well, you can, and for that reason, people have now come up with what we call non-drip brush or non-plating and anodizing. This just shows you the differences between tank and selective. We do the selective plating in place. In fact, you do even use selective or brush plating when you're doing tank plating, because inevitably there's somewhere on that component where you have to have an electrical connection. So that bit doesn't get coated. You have to touch that up afterwards. That always happens. But, as soon as anything gets out of that tank and gets into the world, it starts getting damaged. And so selective plating is important. Okay, next. And here's just an example of plating a big thing, a big aircraft landing gear. You don't have to be bold to do it, but this guy does. All right, next. But when you do that, if you're not very careful, you get huge thickness variations. And so you can see, that red is showing you, where it's particularly thick, which is the edges and corners. Blue is where there are internals and areas like that, and it's very thin. And so this was for some work that we did for a client where they were going from cadmium to zinc nickel, and they had to say, so what do we have to do with the zinc nickel? How do we plate properly? So next. So this just shows you what happens. On the left, you've not put in any extra anodes or anything. On the right, they put all kinds of auxiliary anodes and robbers and other things there, so as to try to plate it as well as they can, as uniformly as they can. The problem
Keith,
yep.
Yeah, Keith, on this one, there isn't the auxiliary anodes in place. On this one, it's showing you without auxiliary anodes how you can have an impact on that nickel composition. How that's
very good point. Yes, right. Yeah. So as Alan says, yeah, on the left, it's showing you what happens to thickness, but on the right, it's showing you something much more important, composition. And as you get more nickel into this system, it becomes more and more noble until eventually it starts corrode. What should have been a sacrificial coating becomes a coating that now corrodes the underlying material. And if you get it too zinc-like, too much zinc, you then get a lot of hydrogen evolution. And in that case, what then happens is that you can get stress corrosion cracking, and the whole thing breaks. So you really got to keep not just the thickness, but the chemistry correct everywhere. And that means you really have to take very careful care over it. And you can no longer just chuck things in a bath. You now have to do very careful design of all your tooling, which is done computationally. Okay, next. Yeah, thanks for pointing that out, Alan. All right, so these are just some of the issues. You can see this poor guy having to plate this. What he's doing actually with the tool here in his hand here, he's plating this special tool down the sides or around the access doors on an F-18. So he's trying to plate all of this area with tin zinc. It's a very complicated, very long-winded job. Next, yep. So in order to avoid having to do all that, you need to catch that liquid before it runs anywhere. So what a French company, a very clever company called Galvanic in France, who we go to quite often for the wine, they developed a technique where they could coat through a coating pad with the liquid with the electrolyte coming into the pad on one area, and then air plus liquid being sucked back out. And if you did that right, you ended up with holding the liquid in the pad and it doesn't flow anywhere. So it was a clever arrangement of controlled flows. So next. How do you do that? You've got this pad, which is actually just white Scotch-Brite, in other words, without any abrasives in. And in the center, there are 3 holes where the electrolyte comes in. Around the outside is a gap where the electrolyte plus air is sucked back out again. And that's very different from the standard tool shown on the right, which is kind of a sock over a piece of carbon, generally, carbon rod. And you kind of wind the sock over it and hold it on, and then you can do your dip plate method. So this is a way that saves you a heck of a lot of time and a heck of a lot of mess. And so we adopted this approach. So next. However, we said, but over all of the time, 15 years or more that Dalek has had this tooling and this approach, they've only ever made one tool until just recently when they made a new one, which was just like the first one, but a little bit bigger, twice the size. In order to go any further, you've got to now do the computational fluid dynamics to show how are you going to balance this thing. And you see on this left picture that the red is the liquid. If you don't balance it right, you have too much liquid coming in relative to air and liquid being sucked back. It goes gloop, and it all goes down onto the surface. And now you have a drippy tool. On the other hand, if you do it right, what you do is you're holding the liquid in the pad, and the only thing that goes out onto the surface is a few droplets, which tend to get sucked away by the tool. So it's a much cleaner, easier way of dealing with things. So this is something that we're now designing entire new tools for this. So next. Okay, so here's a tool design that's not a lot bigger. It was just to demonstrate that, yes, you could do it. And this is an anodizing tool. And so on the left, again, it shows, you know, the way that it doesn't drip. You end up with the electrolyte comes along the surface of the pad, and that's exactly what you want. But that took, you know, a fair bit of care in calculating how that anode is, how that electrode is going to work. So next. All right. So then people saw this and said, oh, that's not a bad idea at all. And as we work a fair bit with F-35, and they saw this and said, we want one of them. We've got these F-35s that are all over the world, some of them on aircraft carriers, some of them on helo carriers, some of them operating at bases everywhere. And we need a way of repairing that zinc nickel that we just put down, that nice new coating. We need to be able to repair it. And especially on that left-hand picture, we need to repair it on planes that have landed on carriers that have got a huge amount of stress on them, and the tires, the wheels have to be changed every 10 launches, or rather every 10 landings, because after all, they changed on board. And so then whenever they do that, there's a high probability of dropping the wheel onto the axle, and that wrecks the coating. And so they needed something that would enable them to do the repair without dripping everywhere, in place, out on a carrier deck, in a howling gale, hopefully not raining, and the carrier is tilting in a heavy sea. So this thing had to hold on a 15-degree slope and all sorts of requirements, which is why you got coating equipment in what's more or less a tank. And the tank is actually made out of aluminum, and it's all got aerospace grade coatings all on it to keep it from corroding, and it has to operate about 20 feet away from the actual tool, so that you're not in that zone, what they call the ATEX zone under the aircraft, where you could ignite the fuel if it spills. So, you know, they're all very careful about all of that. They hate losing planes to ignited fuel pools. So you know, this was a very important thing to them. So this is now, we're now selling 50 of these units in the next year. Next. All right, where else can you use this? Well, the Navy is now replacing its old aircraft that it uses, the P3s, for coastal surveillance, with new aircraft that are actually made by Boeing, and they're a 737 design. So they're a militarization of a standard aircraft that we've all flown in. But they have static ports, like all aircraft do, that contain the sensors that tell the pilot how high he is, what his attack and angle of attack is, and so forth. And they kept corroding because, where a passenger plane would never do this, but this plane flies quite often low over the ocean. It's a sub hunter, so it's looking for things that are very hard to find, and as well as drug runners, which are easier to find. Except they've now begun to come up with submarines too. So this plane tends to corrode very easily on those static ports, which are necessarily open, not painted. They had problems with the engine inlets, same deal. Problems with the wing, the trailing edges of the leading edge flaps, various areas on this plane. And they need a lot of anodizing and a lot of coating. So next, how do you do that? Well, all right, I think as you press the buttons, it'll just show you the different things. You mask the whole area. You deox it, that is, you clean it up very carefully. This is one of the techs, one of the engineers, and then you put on, you mask, you put on, you finally are ready to plate it. And now I just said this non-drip coating, why has it got a drip pan underneath? Well, if you go to the next slide, we discuss that. Nobody wanted the risk that any chemical would run down their plane on the first time you try this. You know, nobody's going to believe it until they see it. also, this is a very small tool, much smaller than we would use in production, and you can't. You can see the way that she's coating, that she's doing this. You have to move the tool over the surface because it's a small tool, and because the liquid, small liquid droplets would tend to coalesce and run down. They have to be caught. And so and a bigger tool would move over those areas and catch them all very easily, but a small tool can't. So she just allowed them to run down into here and then suck them back out with the tool again, carried on using it. But anyway, this now is very very successful. There's been no corrosion for several years now on the test systems. So next, all right. So now we're now going and expanding this anodizing to other areas. We are now shortly going to be under contract to do anodizing repairs on the floors of C5 aircraft, which are our biggest aircraft, big enough for 2 main battle tanks. Luckily, or big enough to play a game of tennis if you want. Luckily, we don't have to anodize that whole floor. We just anodize the areas around the patches where things have gone through the floor. You know, an edge of a pallet, something like that has damaged the floor. They have to repair it, and that requires you take off the anodize. So they needed the anodize put back on again. So that's something we're just about to start now. And next, I think it just shows. You know, why don't we just go through this just real quick? Oh, I think this one's an automatic one. There are 2 ways that you can do a repair like this. You can do kind of a butt repair, or you can do an overlap repair. And the overlap repair works far better. It makes sure you don't get any corrosion and damage around the periphery of a repair, which is a common problem. So even anodize on top of anodize works. And so you can make a really good anodize repair, which is what we do with this. So next. And then that anodize is very good. This is electrochemical impedance spectroscopy. It shows how easily the corrosion will occur through the anodized layer, and it shows that we have very, very high impedance. You know, 10 to the 7, 10 to the 8 ohms per square centimeter. Very high electrochemical impedance. So it works very well, just the same as a regular anodized layer does. But as Alan was saying, you put that in a galvanic situation and it's going to fail. Just, yeah, eventually. Now we had to prove, of course, I think if you click that thing, it'll go. You have to prove that it's not going to go through the holes. You know, all that acid is not going to flow through those holes. And so this is actually a section of floor that we're anodizing here, and you can see that even though you got this liquid on top, nothing is coming through the holes, which was a critical thing. They don't want this dripping sulfuric acid dripping into the underlay of the plane. And so we actually have a drip check, and yep, it was fine. No drips anywhere. So it works. Next, even across the edges. So now we've let ourselves in for having to make a piece of equipment that does this in a reasonable time. But it's small enough to go through a small door on the side of this thing, so they don't have to lower that huge, great big tank door at the end. So in this case, we then have to make a tool that's a reasonable size that will do it. It will do the repair in 15 minutes. And so we're developing that for the floor, and there'll be different sizes and shapes if we need to do inner and outer mold lines on the outside of the aircraft. And this one, we have to actually use a cooler, because otherwise it's going to, with the extra power, it's going to overheat, and that won't make a good coating. So next. All right, but that isn't the only place where you can use this. This is an example of anodizing a friction stir weld in aluminum, which is used for everything from large aluminum tanks to space rockets. And friction stir welding is a very nice method, but it corrodes like crazy on the beach. So the top is what we brush anodized. The bottom is what happens if you don't re-anodize the material after you've done the weld. So it really works very well, that speech exposure. Next. Oh yes, now these are always fun. One of the fun things about working with the military is you get to go and climb on planes. So here we are climbing on top of one of those C5s, and these are quite old aircraft, and they have a problem on the wings that the fasteners are beginning to corrode. Well, they do corrode all the time. If you take the next picture, yeah, this is us actually climbing Mount Everest with Indian Sherpas and everything else. At least that's what it looks like. We're actually walking along the wing here with all of our safety harnesses on. They tell me that if you do slip off with that safety harness, you're probably not going to, you'll probably strangle yourself anyway, but I decided not to test it. So if you click again, I think you'll see what these things look like up close. Hundreds, thousands of fasteners all up this wing. Every single one of them, the cadmium is coming off or has come off, and around the cadmium, you've got damaged anodize. How the heck are you going to plate that? How are you going to repair all that? And we've just been informed that we are going to be getting a program in to demonstrate exactly that kind of repair. If you click the thing again, I think you can see what else. This is something else you can do. You can actually play cricket. It's big enough for a cricket pitch up on a wing like this. We couldn't get them to let us do that because Americans don't play cricket. So here's another example of another thing that Alan's been working on a lot, which is a dry storage canister for used nuclear fuel rods. Once they're used, they're depleted, they store them in ponds, can't keep on storing them in ponds forever. So now they're making dry storage canisters, and then they are storing those in in great big concrete revetments like this. But then the problem is, how can you be sure that's going to last 50 years, which is the length of time they have to last? So next, what we do, and even if you could coat them with something that will make them last, how the heck are you going to do that? This is actually a computational model of what one of these looks like with fuel rods in it. It has very variable temperature over its entire outside, temperature profiles, and that'll change over time. And the thing is made of rolled steel, and that has to be welded. And so you've now got to cover those welds because that's where it's going to corrode galvanically, because the welds are different now in material from the stainless around them. So next, yeah, and you've got to do this, it's got to last for 50 years. How are you going to know that? So what we do is we put all of our computational modeling expertise into it. You have to think of the weather prediction over 50 years when they can't tell you what the weather's going to be tomorrow, the temperature profile and how that changes over time, the temperature and humidity, how that changes with time in the day, season, and long term. If you're near a sea, which is what a lot of these nuclear power stations are near, seawater droplets, they're going to come in, they're going to flow it, they're going to deposit salt particles on this thing. And then as it cools down, you're going to eventually reach the point where water will condense over it. And then you will put all of those salts, and they're not just sodium chloride, the calcium chloride and other things, into solution. And then they'll heat and cool, and it'll go through deliquescence, efflorescence, going through very concentrated salt solutions. And you've got to calculate all that and say, okay, over time, what's going to happen? Will my coating, what coating should I use? And B, will it last through all that? Okay, so next. So this just shows some of the data you're taking into account. You know, the different temperatures at which coatings will, at which the different salts would deliquesce, turn into solution, and so forth. The shell temperature, the outside of that thing over time, over 100 years storage. And you can see it cools down. So you're okay, all the while it's warm. Good and hot, that keeps the water out. I mean, yes, the salts will come down onto the surface, but they won't go into the solution. It's over time, 20, 30 years down the road, that happens. That's the problem. So next. So, first you have to choose the right coating. This just gives some examples using a nickel or a copper electroplate. You can see the copper would last long enough, to start with anyway, without going through all of the calculations. It looks like it will last long enough, and it will not give you galvanic corrosion against the steel. However, it looks like we need an alloy to pull those curves together. But now the curves also depend on temperature and on concentration. So this is a very complex problem. Next. So how would you deal with it in practice? You would either coat them using little tanks, movable tanks, or probably more likely use a tool that we just move up and down and around these welds, because we don't have to do the whole tank. The Canadians actually do the whole tank, and Alan's calculated what happens when you do that as well. So that's another option, but we don't really want to do it that way, or at least the Nuclear Regulatory Commission here doesn't. And so we're now have begun to think about how would you do this. Next. So really, when you get to this kind of problem, this involves every single thing that we know how to do, from thermal analysis, corrosion analysis, the computational thermodynamics, computational electrodynamics, fluid dynamics, and everything else. Kind of a big step from the Wright Flyer. So that's really where we are now. Questions? Thoughts?
Yes, there are some questions, Keith. There are even some questions that you've posed.
Yeah, well, we always do that in case somebody said, I don't have any questions.
Yeah, so we'll go through the questions that the audience have posed.
The real questions, yeah.
Yeah, well, we've got a couple of those at least. Pamela, are you going to do it?
Yes.
Yeah.
There's a question from Peter Darnley, and it is, what is the optimal nickel content for a good zinc nickel coating?
Oh, the optimal coating. Okay, yes. The optimal is about 15 weight percent nickel, which is about 16 atomic percent. At that point, what you've now got is a single phase gamma phase zinc nickel alloy, and that gives you the highest hardness, the best corrosion resistance, and you're not going to have different areas with different zinc nickel contents, nickel contents. So that's the best coating. In brush plating, you have to have less nickel because you have less control over all that, and so brush plating coatings are 13% nickel.
I could kind of argue that hardness, if you're trying to emulate cadmium, for example, that performs very well because it's very ductile.
Yep.
And self-repairs. So in a way, from your zinc nickel, you probably want something that has the ductile characteristics of cadmium, perhaps. I don't know.
Yeah, well, that's certainly a very good point, which is why zinc nickel. I mean, CAD is great on bolts precisely because you can screw them in and it just gives. But zinc nickel can't do that. And so you immediately say, "Oh, does that mean there's a fatigue problem? Does that mean that we've got we could easily get stress corrosion cracking?" And the answer is, well, if you're careful the way you do it, yes, you don't get stress corrosion cracking. The fatigue is not bad because even though it's a hard coating, it's not like it's not like hard chrome, which is really bad for fatigue. But for zinc nickel, if it's hard, it means it will stand up to getting damaged, much better, and that tends to be there are places where that's bad and places where that's good, but we're kind of stuck. We can't use CAD anymore, so we have to use something, and we can't use zinc, which would be nice and soft too. not on aircraft anyway.
Yeah. Okay, Pamela,
kind
back
of stuff.
to you.
Another question from Kathleen Brook. As the tool is so small, is there not the risk of applicator error in the form of missed spots causing small areas of localized corrosion? Why not use a larger tool?
Oh, well, that's where we're going. That's exactly why we're developing much larger tools. Like we've gone to a 3x6 tool for going around those floor patches, and that's because that's a compromise in size. But start thinking about those cricket pitch long wings. Now you have to go to a much larger tool but it has to be long and thin, so that it goes up those whole areas and plates and anodizers as it goes. So yeah, you can miss spots. A good operator though will go over and if it's a difficult piece, like with those P8 static ports, the operator developed a specific way of doing it so that she was sure that she went over everything. But you're right, you can miss spots if you're not careful. But a small tool is good for getting into the awkward areas. So you really need small and large.
Thank you.
Last question from Dominic Shore. If you repair the anodic coating without removing the old coating, is it hard to quantify the exact surface area of the aluminium alloy exposed from the damage? And is it difficult to assess how much current must be applied to provide a suitable coating? Or is this a process potentiostatic?
Right. Well, what we do is there are two ways to handle this problem. You may remember that weird little video that we had of how you do masking. You can mask an area, strip the chemically strip or mechanically the damaged anodized from within that area. Then you make a new mask outside that, and now you've got an overlap area and you've defined the area that you're coating. And so that way that's the best way to solve the problem. For the floor anodizing, the areas are really not that well defined, and so you don't have to get it super accurate. So we think we can actually get away without masking, which saves time and trouble. But you do have to overlap.
Yeah, something to add with that system. We didn't show a photograph of that system. It's got the D2020 has the computer interface, and we track all the current that's actually delivered. So at the end of the process, you know exactly how much current was delivered over that time. Of course, current won't be delivered if you're plating over or if you're going over a previously anodized surface.
Yeah, you can anodize a bit more over the top, but you're not going to anodize the full thickness. Yeah.
Right. So you'll know at the end of the repair how much total current was delivered, and you'll know how much acid you used and everything. You have all that information, and of course you can make some measurements as well to check thickness.
Mm-hmm. Yeah.
We could do now is we could take the crib questions that you sent us in case nobody asks any questions, which they have. But
I think, Alan, there's no need. We used to
we might
kind of chair in meetings. Go ahead.
We've set ourselves a cutoff of 6 o'clock here, so.
Okay.
Yeah, but I mean, people don't need to stay. I mean, I think we just thank everybody for coming. It's a really nice turnout, and we're going to put this available online on the network website. And Pamela's encouraged you all to register on the network because all of the webinars that we've run are available on there. Mm-hmm. Let me just ask these questions because they're worth asking. How difficult is it to do the computational work? Is the first question.
Okay, well, so the workflow had started from like the Corrosion Gin, and you saw me demonstrate that. So that's very easy. Like Keith said, even he can do it. And then we're trying to simplify, you know, those standard joints and so on. So it's almost just like putting numbers in a spreadsheet. Oh, this is the diameter, this is the size of some typical kind of geometries. So they should be straightforward as well. It gets a bit more difficult when you start importing the actual CAD of a system. But if you know, many people can work with CAD systems. If you can use SolidWorks, you know, CATIA, or if you're that way, you know, inclined, then doing these corrosion analysis isn't, you don't have to add substantially more skills. And it's very quick as well. Even the 3D calculations are very quick. So varying skills requirement, but not extensive.
Okay. The second question, what kind of PPE do you need to do brush plating?
Well, generally.
Go ahead, Alan.
Okay, yeah. So yeah, with the PPE, there's a good point here. With the Dualistic, if you recall, we have electrolyte being supplied to that porous pad, and then we have a second pump in this whole unit that kind of sucks back the excess electrolyte and a much higher volume rate, because it also sucks back ambient air. So with some processes, you might have some off gases and some you know, some smells or whatever. And with the Dualistic, we did do some measurements where we had monitors on the shoulders of the operators, and because the air was being sucked locally at the point of application of the repair, there was less kind of contamination in the air, so we didn't need local additional ventilation. So basically, gloves and glasses. You don't often need additional local ventilation, particularly with the Dualistic.
Yeah, and none of those great big thick vinyl thick gloves and aprons and all of that stuff. You don't need that.
No, that's not a problem.
You know, so it makes it a great deal more comfortable for the operator.
Yeah.
There is another question here from the speaker, from the viewers. How to predict at the design stage corrosion over an aircraft life, or at least until the overhaul, knowing that an aircraft is designed to fly in different locations of the world where the environment could be diverse?
Okay. Do you want to do a stab at that, Keith? Because that's something that we're kind of embarking on, really, isn't it?
Yes, we are just, somebody has just, the Air Force has just asked us to do exactly this. So, yes, the DoD, the Department of Defense, actually has what they call corrosion severity indices for all over the world. How nasty is corrosion everywhere in the world, from the deserts of Arizona to the jungle forests of Guam. And so as planes go around the world, or ships go around the world, you know what kind of environments they're encountering. And so then what we can do is we can take those corrosion severity indices and work backwards to what that means in terms of our computational methods, so that we can say, all right, this is what is going to happen given this particular kind of usage of this aircraft. And that can take into account the environments it sees, whether it's inside or outside the aircraft, and even things like wash cycles, which is where they wash these aircraft off to get the salts off them. So you can do that kind of analysis. And so we're just trying to get that. We're just starting out on something for the Air Force along exactly those lines.
Great. Kathleen also asked, will the slides be shared? Well, of course, this webinar will be available as a video online on YouTube. Probably, with your permission, we'll put the slides available as a PDF on the network website. Is that okay?
Yeah,
Oh, yeah.
Yeah, we can do that. It's public.
Yeah, and PDF is going to be the only reasonable way to do it, I think. Yeah.
Thank you.
Well, yeah, we can strip out the some of the movies and deliver you a couple of PDFs for that.
Yeah. There was one other question that you set yourselves. What problems do you have when zinc nickel is nickel rich?
Oh, I think we already covered that
Yeah.
bit. Yeah, as it becomes nickel rich, it goes above the open circuit potential of the underlying steel it's supposed to protect, and now it starts destroying the steel instead of protecting it. So yes, you don't want it going nickel rich.
Mhm.
Okay, that's great, guys. I think we've completed, and I really like to thank you once again for doing that. It's been fascinating, a fascinating insight into the practical world of corrosion protection and the developments in some of these techniques, particular electroplating techniques, which normally you wouldn't think of as being mobile, and you've made them exactly that. I mean, I know you did it for HVOF.
Yeah, right.
when people were looking for a replacement for hard chrome, and you developed, I know, Keith, you in particular developed HVOF systems which could be taken to the location and applied with great success. So, I mean, all I can do is thank you once again, and say that when you're ever back in Manchester, you're always going to be welcome.
Okie dokie. Yeah.
Okay, great. Thank you very much.
Let's
Have a
hope
good weekend.
Yeah, and let's hope that's not too far away.
Yeah, hope
Okay.
not.
I'm there at Christmas.
Yeah, right.
No, we're hopeful.
Yes.
Freedom Day on the 19th of July or something.
I was supposed to be coming over in August, but I ended up cancelling that because I wasn't so sure about the COVID system. So I just kicked the can down the road a bit. So hopefully Christmas, I'll get to see my family. Bye, guys.
Okay.
Great stuff.
All right.
Very much.
Thank
you.
Bye.
Thanks.
Thank you. Bye-bye.